start recording of the session also. So, and have been extensively training people from Design Pathshala, and I think we have trained more than 1,000 people myself in Design Pathshala and different courses for big data. So it's been good till now, and hopefully you will be also liking the course. So I'll hand it over to you. I'll just request a brief overview from yourself about yourself, what you are doing, what you are expecting out of the course, and your familiarity or your technical background. So I'll hand it over to Mahesh first.
Okay, this is Mahesh Bapai. I'm located in San Francisco Bay Area, and I'm working in the technology industry for over 35 years now, and all throughout in IT. Most of it is in Oracle related technologies, Oracle apps, Oracle middleware, Oracle database. I'm currently working at HP and working as an architect, and obviously I'm trying to get some upskilling in terms of today's technology. So I have got good familiarity with some of the big data related technologies like MongoDB, and so I've done that from administration point of view, though I understand this is a development course, and I'm looking forward to learning more on or learning about Hadoop and how it can be used and how I can really get more knowledge to basically put me in a position of strength as far as my role of as an architect is concerned. So,
Sure, definitely. I will definitely try to help you in that part. And just one more thing, any familiarity with any of the programming languages?
yeah, in the sense, I know a little bit of Java, but mostly programming in terms of means PLSQL, then means mostly Oracle related, right?
Okay.
But then, of course, means the fact that I've been in this industry for
Yeah,
over
so
30 years,
you would have seen
that
different
means
flavors.
yeah, right from COBOL to
Yeah.
today's languages. So, but mostly my role is more of architect and management. So really, I'm not for some time I'm not doing all hands-on work, but at the same time, getting to know the technology is really important. So I don't see programming as a showstopper for me.
Sure, sure.
Yeah.
Actually, all I wanted to look at is if you have been into any of these things, and understanding the things would be easier. That's all.
Yeah,
Yeah,
no problem.
sure. Thanks for that, Mahesh. I'll hand it over to Suraj.
Hey, so this is Suraj here, and I've been with the IT industry for the past 11 years. I was working all my life. I worked in the telecom domain. I was working for Verizon for 11 years, and recently I joined Cognizant, and I'm currently at Miami, Florida. Prior to that, I was in Dallas, and since it's a telecom company, so like it's kind of a lot of like legacy applications. So from the environment perspective, I was working on like kind of open systems with like C++, and then later on like product specifics to like Ericsson. So the hands-on for me from the technology perspective will be like pretty much in C++. I never got a scope to work on Java as such because we were working mostly on the products to develop the two like applications for Verizon. So I will be using this as an opportunity for me to groom myself up for the like future technologies that are coming up in the market.
Sure. Yeah, that would be great, and I hope you will be getting that. So although people keep on saying Java is required for learning big data, I know that Hadoop is written as on big data, and the native framework or MapReduce runs on big data. Oh, sorry, native framework runs on Java. But don't worry about those parts. The most of the implementation which is happening in the industry is happening on frameworks which are written on top of MapReduce. Those are big and Hive kind of things, where you don't have to write a single code of Java line, and you can process your data with the help of SQL kind of language, or with the help of scripting languages. So we'll be talking about all those things in some time, and hopefully it will be great. So it looks like it's just two of you. No one else is joining in. So we can start up. Any other questions before we start up?
Just a quick question on how you plan to kind of run the labs or kind of exercises and installing. I'm pretty sure you will go through that, but just
Yeah.
and if you are going to cover it later, don't waste your time right now. So I'm okay. I can wait. But
Okay. Yeah.
so
So, definitely. So for the labs, another thing what I'll be requiring. I'll be sharing you the virtual VMs, pre-configured VMs, which you can directly put it in our laptops. How to install that? I'll be sharing you, and that's all documented over there. So I'll be
perfect.
sharing you a folder on Google Drive. So I'll just request your Gmail IDs so that I can share you all those things on the Google Drive. And these PPTs also, which I'm discussing right now, will be shared on the same drive, as well as all the code which I'll be walking you through will be lying on the same drive. And after each session, like after covering MapReduce, Hive, or Pick, I'll be giving you problem statements which you can try either in the class or later on whatever is convenient to you people. And we'll be discussing those things. So everything will be shared on the same drive folder. So I'll just request you to ping me your Gmail IDs, and I'll be sharing you those things after the class.
Okay. Okay. Perfect.
And how to install that part, and what to do, don't worry about that thing. So we'll be discussing that thing either into tomorrow's session or in the third session. So how to use them, how to install them, I'll be helping you all those things. You can just download them, because downloading that thing will take time, because the total size is around 5 to 6 GB. So you can just keep on download that, and later on I can help you how to solve it. Okay, so let me quickly walk you through who we are, what we are doing. So we are a group of expert trainers across different domains, and have been teaching people across the world, mostly from US. And we don't have any classroom trainings. We just provide online trainings. So most of our professionals who are teaching under the umbrella of Design Pathshala are working professionals, and that basically helps to keep maintain the quality, because these people are have really burned their hands into different technologies and have been into the touch of the new things come in the industry. So that makes our quality better. We don't have trainers who are freelance kind of trainers, because they are not acquainted to what's going on latest in the industry. And as the people are really working into the industry, so people can really talk to different real life experience which they are facing in their real projects, and they can basically share those experience with you. And that's how we try to make you connect and basically learn and apply kind of thing. And you can browse a lot of courses on our website. At a time, most of the courses might be disabled, the enrollment might be disabled, so we keep on starting the enrollment based on the batch creation and different things which admin will take. So but there are a lot of courses on the website, and there are a lot of things which are related to cutting edge technologies, and we offer different courses. So that's all from about us. I'll browse into the course which will be covering up. So I will be starting off with motivation for Hadoop. What exactly is Hadoop, where it's used, why it's in so much, if euphoria about processing of big data kind of thing. Then moving on to the MapReduce. So the MapReduce is a framework which helps you to process the data on Hadoop as a file system, HDFS as a file system. So we'll be looking at MapReduce. MapReduce is all in Java. So if you're not aware of Java, don't worry about that part. And just try to understand the concept, how the processing of the data happens, how the different components interact with each other to process your data. Don't worry about the complexity of the Java code. Believe me, you will not be using MapReduce in your real life experiences. In 3 years of different projects which I implemented to productionized versions, the percentage of MapReduce code written over there is not more than 1 or 2%. That's also to some peculiar case which is required. The MapReduce need to be written up. But rest everything, rest all the processing happened. Sorry. Rest all the processing happens just by using Hive and Pig. So Hive is basically a kind of SQL language. So Hive is a framework which at the backend generates some MapReduce code for you and do the processing. You as a person interact with the system with the help of SQL kind of language. Select the star from table so and so, where clause so and so kind of things. Pig is a scripting language. So if you are aware of any scripting language, it's much similar to that. There's not great syntax. We'll be looking at that thing in detail in the Pig session. Thereafter, we'll be looking at Scoop. Scoop is a framework which is again helps you to get in the data into the ecosystem and export the data out of the ecosystem. So how to get your data into big data system and export that thing. That can be done with the help of Scoop or Flume. Then we'll be looking at Oozie. So Oozie is a workflow. So you can create your whole workflow with the help of Oozie, and you can stitch in Pig, MapReduce, Hive, Scoop kind of things in your workflow, and can schedule them with the help of Oozie. So we'll be looking at the Oozie as a workflow engine. And I'll be walking you through the Hue concept. That's UI from where you can browse the system and do different things. So this thing will be keep on doing. And finally, we'll not go deeper into this side, but I'll give you a little brief of how you basically visualize your data or do analytics on your data after connecting different visualization tools to your big data world. And at the end, I'll be giving you a final project which would involve most of the things which we have discussed in the class, and you can develop that project. And once you are done with that project, then we can have a final class to discuss that if you are facing any issues and what all could be improved in the project and things like that. And once the project reaches a satisfactory level, you will definitely get a certificate from Design Pathshala also. Any questions, anything on the spot? Anything which you were looking for, or anything?
No, this looks good to me. This is exactly what I was looking at. So, final project, are you going to kind of develop it through the course, or it's just at the end when?
No. So final project basically, until and unless you don't understand the whole ecosystem and different things which are happening at different places, that would not make sense. So final project I'll be giving you at the end only, but that will be really involving most of those things. It's up to you. You can either use totally Pig to do that. You can use only Hive to do that. It's up to you how you can what you want to use. You can write it and all in MapReduce also. It's up to you. You have to think of what is the best thing which you can use to do the thing. So that will basically make you think of or basically revise the whole thing what we discussed in the whole session.
So you will be giving it at the end. So then after the course completes, also we can kind of work with you for maybe a week or two to complete that project, right?
So what we do is you try to do that, you do different things, and if you're facing any problem, you can just drop me an email. And once you are done with some things which can be discussed, then we'll have a class and we can discuss the problem which you're facing, or if you have developed what you have developed, we can discuss those parts.
Okay. Okay.
So okay, so let's move on. So if you remember, I think Mahesh would have definitely seen those words, and Suraj you also would have seen because you are also in the industry from last 11 years. So if you remember your school days or the time where it's just a single computer and the operator used to sit on it and try to enter your data. At that time, the data was not there in the system, and your single PC was sufficient enough or capable enough to handle your whole data, and we were good with that part. And if you remember, there were floppy drives like this of 2.5 MB or 3 MB, and that was much more than sufficient for us to carry our data. So we have seen that era, and the hard disk of the PC was not more than 512 MB kind of thing, and that was much more than sufficient. Nowadays, 16 GB of the RAM on the PC is not even sufficient. So the data is growing at an enormous rate, and the problem with the word is how to handle that data. The data contains a lot of uh, information. That data can really mint a lot of money for you, but the problem is how to handle that data, how to mint the money out of the data. So that the world is changing slowly and slowly. Now we have moved on to the world of Facebook, Twitter, and LinkedIn kind of thing, and it's not just the operators or uh, the persons who are just entering the data kind of thing. Now we have moved on at the users who are interacting with the systems real time and generating enormous amount of data into the system. And uh, due to the sudden change in the scenario, the data in the systems is increasing at an enormous rate, and the data itself has become a problem to the systems. So how basically we can solve this thing, or what to do with that thing? We'll be looking at those different things on how to basically process this enormous amount of data, which is now coming to our systems. So I've highlighted one picture on the on my PPT. Any guesses what this picture could be doing over here?
Meteorological data, weather related data.
Yeah. So the satellites, it's not only the user generated data which is a problem to us. The next bigger problem is the machine generated data. So the data which is generated from the machines is again generated at an enormous rate, and to process that data or to come up with the predictions. So what is the weather at 2 p.m. Today at Miami? If I have to predict that, I have to process might be 20 years historical data along with today's data to predict what could be the weather at 2 p.m. today. And that's not only the data. I might have to process other geographies data also, so that I can figure out what could be the weather at Miami today at 2 p.m. So the data is generated enormously from these machines, and to use that data, I have to process enormous amount of data. What could be this doing over here?
Sensors in the aircraft generating a lot of data.
Yeah. So a Boeing aircraft has 4 engines. Each engine generates approximately half a terabyte of data in half an hour flight. Oh, sorry. Yeah, in half an hour flight approximately. So if there are 4 engines, you can think of a flight from New Delhi to New Jersey could be what kind of data that could be generating. And if you have to look at the data, process the data, you can think of how much processing power is required just to process the data of single flight. And if this kind of data is generated daily, and how the airlines could be using the data. So if there are few flight related incidents in the recent past history, some of the flights go getting disappeared. So if you figure out the black boxes of those flights, you can think of the kind of data which you have to process just to find out what could have happened back to that flight. Hospitals are again generating enormous amount of data, not only from machines, but from doctors, from researchers and different things. So they're using the data to predict the diseases which can happen in to you, or based on your genetic history and things like that. Pretty interesting. So okay, it's not only that thing. Now, this picture definitely gives you an idea what I'm talking about. So people like Amazon, Walmart, they are generating enormous amount of data from their sales. The kind of sales these people are doing are more than a million transactions an hour. So if they have to use those things to find out or do kind of market basket analysis. Okay, so what is market basket analysis? Anyone has any idea what is market basket analysis? Okay, I'll give you an idea. So before that, let me give you one example. So there was a vegetable vendor who used to visit near to my society, and I really used to buy some fruits and vegetables from him. And someday later on, he really did not he was not coming to our society, and I also forgot that there was some guy, and I used to buy from someone else. Around 8 9 months back, I shifted my flat, and I've shifted to a society which is not far away from the previous one, but the locality is much better from the previous one. I use this. I saw the same vegetable guy downstairs, and I asked him, "Hey, you used to visit that place. Now you're shifted to this place. So what happened?" The smart answer which he gave to me is, sir, the people over here are carrying cars like Audi and Mercs and Lamborghini. They have more purchasing power, and they really do not bargain much for me, and they really buy more products as compared to there. So I can sell products at a premium cost as compared to there, and my sales has increased over here. So I have shifted my geography. But now, if Amazon has to do the same thing, you can think of what they have to do. They're doing more than billion transactions an hour. So if they have to figure out such kind of things, so what is market basket analysis? Market basket is analysis is if a person is buying the so and so product, what is the probability of him buying some other product? So Walmart came up with a pretty interesting market basket analysis, I think 2 or 3 years down the line. If beers and diapers are placed together, the sales of both increases. So in most of the Walmart stores, you might see beers and diapers together lying. So if these kind of analysis are done on the data, that guy has pretty smaller geography and pretty smaller data, so he was able to do that kind of analysis. But if such kind of analysis need to be done on millions of transactions an hour, we really require something which can do those things. So the major challenges with the system is not only the volume of the data, but the velocity and the variety of the data also. So what's volume, velocity, and variety? We'll look at those parts. So the volume, I was just talking about the volume of the data which is lying in the systems or which is getting generated in the systems. So if you look at whole World Wide Web, these figures might be little older. They might not be exactly what is the current data size, but I'm just trying to give you a little just some idea. So the World Wide Web itself is sitting at more than 3 gigabytes of data. The Library of Congress is sitting with more than 300 terabytes of data. Facebook is sitting up with 30 plus petabytes of data. This figure might be pretty good. Walmart, just about their data warehouse. I'm not talking about their real transaction systems. I'm just talking about their data warehouse is sitting up with more than 2.5 petabytes of data. eBay, 10 plus petabytes of the data. So this is the kind of data on which people are setting up with, and if they have to do such kind of analysis or such kind of processing, they really require systems which can handle such kind of data. So the next challenge is not just the volume of the data on which people are sitting up with, it's the velocity at which the data is growing. So every minute there are 48 hours of new videos which is uploaded to YouTube. So if YouTube have to process those videos to look at if those videos are adhering to the YouTube policy or terms and conditions, they have to process 48 hours of video in less than a minute to come up with such kind of analytics, or such to basically follow, make people follow their terms and conditions. Every minute there are 571 new websites which are launched, so Google have to process them at a much faster rate. People are putting up different posts or media kind of thing on Facebook at a rate of 500 plus TV per day, more than 175 million tweets per day, 1 plus million of transactions every hour on Walmart. So it's not only the volume, it's not on the volume, it's the velocity of the data which is the next bigger challenge in this world. And it's not only the velocity which is a challenge. The next challenge is the rate at which this velocity is changing. So the acceleration of this velocity is again a problem. So the rate at which this data was getting increased in 2009 would be 44 times greater in 2020. So this velocity itself is increasing at an enormous rate. And the third biggest challenge is the kind of data which need to be processed. So it's not only the structured data which need to be processed, because the data is getting generated from users, the data is getting generated from machines, the data is getting generated from different sources. So it could be semi-structured like JSON or XML, or it could be totally unstructured like your documents, emails, tweets, and things like that, videos, or machine generated data. So if you have to process unstructured data, you really require more processing power to process your data. So before moving ahead, let's look at few of the interesting things, how people are really minting this data processing, and how companies are using big data at different phases or different stages to mint money. Any question on the previous part before I move it? I hope there was nothing great over there. Okay.
It's okay. It's okay. It's a good start. So go ahead.
Sure. So, so predict what exactly customer wants before they ask for it. Log into LinkedIn, log into Facebook. They will suggest the friends for you before you search for them, based on previous history and previous things like that. Just give. So basically predict what exactly customer wants. You log into, you search for any product on the website, or you search for any product on the Amazon website, or any of the e-commerce website. Go to any other damn website, you will see an advertisement of the same product somewhere on the left or right, popping it up. So based on your searches, based on what you're looking for, based on history, the people are really trying to predict what you want for before you really ask for it. Marketing campaigns. It's not only the marketing campaigns are not like how they were used to be previously. Now companies are trying to really target the potential customers, and they are using the data which align with them to figure out who could be my potential customers, or how, if the customer is not getting good feedback, or not getting good I'm not getting good business from customers, I will try to market him more. So people are doing targeted marketing, improve customer services to buy any product, or let me give you an example of Delta Airlines. So what they did is, the most pathetic thing, if you're flying international with a halting flight, the most pathetic thing, or the most really occurring thing, is your loss of baggage, or baggage get misplaced or departed at your halting station kind of thing. So what they did is, they created an app called Track My Bag app. What you have to do is, you have to just click the bag and the corresponding tag on the bag, and upload it to your app. If your bag is lost, or deported at some other station, the app will track your bag and will really tell you where your bag is lying. So although they are not able to solve the problem of bag getting deported at different port, But now you know where your bag is lying and how much time your bag will take to reach you. You will not again and again call their customer service and trouble them, and you also will not get troubled up because you can see or you can lively track your bag. Getting customer excited about their own data. There are different companies different websites which are selling dairy product. So what they do is when you buy a product from them, they track how much calories you would have consumed by eating those products. So now you know how much calories you have consumed by eating the product. You would really love to buy a different product from them only so that you can track your whole calorie chart and kind of things, those kind of things. So they are basically, getting customers just excited about their own data and trying to increase their sales. Identifying customer pain points and solve them. Social media graph is highly used. Um, there's a website called Flipkart, pretty prominent in India. I give you an example of them. I brought a product from them. Due to some different reasons, the product was faulty. I tried to call their customer care, but the experiences which people really face with customer care. So I just placed a post on their Facebook page stating what I was facing up. And I did not place my phone number, I did not place my email ID, I did not place anything. I just placed a angry post on their Facebook page. That's all from my Facebook ID. Within half an hour, just within half an hour, I got a call from their customer care department. Sir, can you please remove the post from our Facebook page? I can understand your problem. Yeah, we are reshipping your product and will not ask you for any refund, anything like that. We are sending you a new product. In half an hour, they were able to process the Facebook posts which are coming up for them. They are able to figure out the sentiment and analysis of the post. They are able to figure out who is the customer, what is the product he has brought in from them just based on my Facebook ID, and they are able to call me up. So this is the rate at which people want to process their data so that their brand images are up to the mark what they want for. Research and development. It's not only the companies who are spending a lot of money, as the government's also spending a lot of money into research and development. The Obama government have recently launched a budget of $200 million plus for the different departments to be using big data for processing the different data which is lying up with them. So it's not only the company who's using this processing, it's the government and the different agencies which are basically trying to mint the money out of the data on which they are setting up. So we have just looked at those things. Facebook is setting up with 30 plus petabytes of data, and they're using this data to analyze what people are looking at. LinkedIn, the people you may know. Amazon looking at your clickstream data to recommend the products. Treato, pretty good thing. They're using the big data to do different research on the healthcare domain. A few years down the line, decoding a normal human genome took 10 years. Now that can be done in just 7 days. And now it's just also reduced to, I think, 1 day. So this is a market of big data, and this is a graph which I took from you can see in 2009, 10, 11, the graph itself is not visible. So the market was very small, but the rate at which this market is growing up is more than 1000%. It's expected to be more than 53 billion US dollars by 2017. So this market is growing at an enormous rate, and you can understand the reasons what I was talking about previously. So the market is growing at a pretty great rate. So these are different roles which you can think of in the big data industry based on your work access or based on your profiles which you were talking about. I think this is the best role which suits to both of you. And this is also pretty interesting role, but this not only involves the data processing, but that also involves understanding the statistics kind of thing. So for that you have to know something like R or any machine learning kind of languages or something like that. We also have the courses on R and machine learning languages. So, but data scientist is a blend of data processing as well as running statistics on the data. Administration is a totally different role, and developer I want to just to based on your profiles. So this is a graph just talking about the different salaries and different. So there's a graph of US salaries for big data. Different companies we have which are hiring for big data. So this is just intended for India only. So let's look at the history of the big data, the Hadoop. So Hadoop was basically evolved from so there was a guy called dog cutting. He was handling a product called Lucene in Apache, and they started. So Lucene was a product which was a kind of indexing. So that basically creates an index on your files, so that your searches on the files or your on your text or on your data is much faster. So while that project was getting created, they started a sub project called Nudge inside the same project. The Nudge was a web crawler, so that crawls the webs, get the web data, and that gets stored onto their systems. And then Lucene was used to index that data. So you can think of what they were creating. They were trying to create something like Google. So the product was pretty ambitious, and the company really wanted, or the management really wanted that to go ahead. So they wanted it to go on a full-fledged scale. So the guy came up with the budgets how the product can go ahead at the time, and they came up with a system requirements where just the maintenance of the system is required $200+ million a month. It's just the maintenance. I'm not talking about the infrastructure of the system. But as the product was pretty ambitious, the management got a go ahead of that project, and the project started. Just 2 or 3 months down the line, they faced problems with the vertical scaling of the system, and they were not able to proceed. I hope you understand what is vertical scaling and what is horizontal scaling.
Yes, I'm aware.
No, if you can explain me, that will be great.
Okay. Okay, so just give me 5 more minutes. I'll explain it. But let me complete this part, and I'll explain it in 5 minutes. So they faced issues with the vertical scaling of the systems, and they were stuck basically. So at the same time, Google came up with a white paper where they published Google file system and how they were processing that data with the help of MapReduce kind of thing. So dog cutting read that, and they thought of implementing the same thing. So they started a project called Hadoop, and they came up with a similar file system called HDFS, that is Hadoop-based file system, and the MapReduce as a processing layer on top of it. And then Yahoo later on hired dog cutting, and you can understand why Yahoo hired dog cutting. And later on, most of the development related to Hadoop was done in Yahoo. And now there are a lot of contributors on different things to this thing. But the brief history about how the real thing started. And Hadoop was, so most of the names that this guy dog cutting gave to these projects are either influenced by his family or by his child, basically. So like Hadoop is a name of a small elephant which his toddler used to play with. Nudge and Lucene were name of his wife, or some maiden name of his wife's mother, kind of thing. So most of the name which he gives are influenced by his family or by his child. Okay. Regarding the vertical and horizontal scaling, vertical scaling is basically you are scaling your systems vertically. That is, you are adding more RAM or processing power to your system. So let's say I have a laptop today of 8 GB RAM, and that's not sufficient for me to run some of the softwares. So I'll add 8 more GB of the RAM, and total RAM in my laptop is 16 GB. So I basically vertically scale my laptop so that I can process more data on my laptop. But what is horizontal scaling? So rather than adding more RAM on my laptop, what I'll do is I'll parallelly add one more laptop, or I basically parallelly add one more system onto my infrastructure, and half of the processing requests are coming to the system first, and half of the processing requests are coming to a system two. So I'm basically horizontally scaling my system rather than vertically scaling it up. And if later on I face some problem in the scaling and I require more CPUs to process my data, I'll add third more node to my cloud, to my infrastructure to process it. So rather than doing a horizontal scaling, adding more RAM to this machine or adding more CPUs to a single machine, I'm scaling my system horizontally. And the beauty about horizontal scaling is you can add as much machines as you want, but there's a limit to vertical scaling always. And vertical scaling is always costly. If you go to the laptop and try to buy a laptop of 32 GB RAM kind of thing, that would be more than $1,000. But you can definitely buy 2 laptops of 16 GB RAM or 4 laptops of 8 GB RAM, and that would be less than $1,000 in the market. So vertical scaling is always costly, and there's a limit to vertical scaling.
Thanks about
So I'll give you a quick mathematical calculation, and that will really help you understand the things. So this is a machine setting up with 1 terabyte of the data, 4 IO operations on your hard disk. So there are 4 IOs to your hard disk. 100 Mbps is the speed of your IO, which is normal SATA speed, which is there on the hard disk. And sorry. So I have to read this 1 terabyte of the data from my hard disk. There are 4 IOs, which 4 IO operations. So 4 IO port on my hard disk. Each port is 100 Mbps speed, the normal SATA drive kind of thing. If I have to just read this 1 terabyte of the data from this hard disk, can you do a quick mathematical calculation how much time I will be requiring just to read this 1 terabyte of data? 4 IOs, normal SATA kind of hard disk, 100 Mbps the speed per IO. I have to read 1 TB of the data.
About 43 minutes 69.
Yeah.
43.69.
Yes. So it takes around approximately 43, or I can say approximately 45 minutes to read just to read this data. There's something called Hadoop benchmark sort which happens up. So Yahoo sorted 1 terabyte of data in 209 seconds. Where I'm talking about sorted, they not only read this data, they process the data, they rewritten the process data into the hard disk, and everything was done in 209 seconds, approximately 3 or 4 minutes. So this is the kind of processing which people are able to achieve, and if you have to just read this data on a single machine, it requires 45 minutes. Prior to that, Google had a record of sorting 1 terabyte of data in 297 seconds, but that was broken up by Yahoo, I think in 2008. So what they use for this thing is they use a cloud which has 910 nodes in total. Each node has your, the configuration of each node was kind of commodity hardware or normal laptops kind of thing, which normal laptops and desktops people normally use. 2 quad-core processors and 8 GB RAM per node. So pretty normal configuration, but they used horizontal. They horizontally scale the power by adding more nodes to the cluster or more nodes to your cloud. They use 910 node cluster. So by doing horizontal processing of your data, they were able to achieve not only read the data, they were able to process the data and reinsert that same data in just 209 seconds as compared to 41 minutes, which we took just to read the data. So this is the kind of processing power which you can achieve by horizontally scaling your systems. So if I have to read this data, or say basically if I distribute this 1 terabyte of data across 10 machines, so each machine is approximately one G, 10 GB of the data, approximately 10 GB of the data. So now you can think of how much, and each machine has the same configuration, that is 4 IO on their hard disk, 100 Mbps is the speed of each IO. So you can think of how much time I would be taking now to read this data. My data is distributed across 10 machines. Each machine is having approximately 100 GB of the data, 1024 divided by 10, approximately 100 GB of the data. So if I have to read the data, now I can read parallelly on the 10 machines, so it will take approximately 4.5 minutes to read this data. So by horizontally distributing my data, I am able to read my data 10 times faster as compared to previously. That makes sense to you, right? Now you're able to get the thing what I was saying.
Yep.
So second thing is, once your data is divided or distributed across different machines, now who knows where your data is lying? How can I read the data? Now the next question comes to your mind is, how can I read the data, where my data is lying? If my data is divided across 10 machines, how will I know where my data is lying? There's something called distributed file system, and we'll be looking at so Hadoop has Hadoop distributed file system. So if say these are the 10, these are the 4 machines out of those 10 machines where your different data is lying up. So let's say in one of the machine my data related to design Pathshala project is lying up. In one machine my data related to design Pathshala images is lying up, and so on. Now who will remember on which machine my which data is lying up if I have to read the data? So what we do is there's something called master in the cluster which knows all about your data, where your different data is lying up, and there's a similar machine into Hadoop ecosystem, what we call name node. We'll be looking into name node and different things in some time. So that master of the cluster knows where your data is lying up. When you read some data, you will just interact with the master, and the master will tell you where your data is lying up. So if your data is distributed across your different machines, you communicate with your master where my data is lying up, and master knows the whole metadata about your data, where your data is lying up, and you have to just interact with your master and with something like this, so the master will tell you basically where your data is lying up. So you just interact with the system by your name is of the system / by your file or the folder which you want to access, and the master will basically help you out with the things. So this is how basically you distribute your data, and if you are able to distribute your data and you are able to read it parallelly, you can process it parallelly also, and this is a beauty which we get with the distributed data. So before moving ahead, so now who uses Hadoop? So there are different companies who are using Hadoop, and the companies are setting up with different clusters. So if I look at Yahoo is setting up with more than 42,000 node cluster. LinkedIn is setting up with more than 4,000 nodes cluster. Facebook is setting up with more than this figure is again I think older, more than 14,000 1,400 node cluster. So this is the kind of cluster which people are using up to process their data. So these are the different nodes on their cluster which people are using up to process their data, and this is how they are able to achieve such kind of processing power which they really require based on the data on which they are setting up. Sorry. So then the machines which are really used in this infrastructure, if you remember whatever I talked over here is, so these are the pretty common machines, or what we call commodity hardware in Hadoop system, Hadoop related terms. So this is called commodity hardware. This hardware is pretty cheaper. So if you so that's kind of the Honda Civic or the pretty commonly used cars. And there's something called master in the cluster which manages the whole cluster. So that's kind of Ferrari or Lamborghini of your system. So these machines can fail a lot. These machines can get powered down a lot, or they could be different issues with the system. So these are commodity hardware which can be which are cheaper to buy, and you can add to your cluster, and you can basically process your data on these commodity hardwares. And how these right. So before going on to that part, so let's look at this formal definition of the Hadoop. I really do not like formal definitions, and I will not be having most of the formal definitions, but this will really make sense to you. So Hadoop is a framework for distributed processing of large data sets across large clusters of commodity computers using simple programming model. So I've explained all of those things. Do anyone want to, iterate what this definition is talking about, rather than I talk about that part?
Yeah, it's very clear. Actually, it's very well defined in one single sentence. That key points, that use of cluster of commodity computers and parallel processing in terms of using that cluster of computers, and what you're handling is a large amount of data. So I think it makes sense.
Yeah. So this is how basically Hadoop basically handles your data. So your data is divided across the cluster. How that is divided, how that happens, we will look into that thing in deeper and later on. So, but the beauty about the system is your data is divided across different nodes in your cluster. As big you can create your clusters as big as you want. The hardware which is used is a commodity hardware, that is a cheaper hardware. So there's no worry about the cost of the cluster. The cost of the cluster is minimal, and you can process your data parallelly across different nodes on the commodity hardwares, and you can achieve as much processing power as you want. You have to just add nodes to the cluster. So if you have written some code, and then your directors or manager will not be asking you how or what will happen if the load in the cluster increases, or how can I scale up the program. All you have to do is you have to just add more nodes or add more processing power to your cluster. There's no change in your piece of the code to process your data.
Just one quick question, if you can go to your previous slide. Not that one, that is before that. Yeah. Now, if you see here, really the 4 nodes on the left are really having individual data, which is not, means images are only on one server, right? Not on all servers.
Yeah. So this is just an example which I wanted to show you. Practically, this will not happen in the cluster.
Oh, okay. Okay.
Practically, the data is randomly distributed across the cluster. But before going into that part, I just wanted to give you a glimpse what is really happening up.
Oh, okay. 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 Perfect. Thank you.
So practically your data is divided into blocks, and that is distributed in the cluster. We'll talk about that part in some time. So, but the ecosystem, or the cluster is created in such a fashion that any kind of you can fit in any kind of data, and the processing happens with help of MapReduce. There is a framework to process your data. So we'll look into the MapReduce I think tomorrow or day after in the next class. So MapReduce is a framework which really helps you to process your data. So now, okay. So what makes us reliable? I'll talk about that part in some time, but you can understand the rest of the terms. It's scalable. You can keep on adding your commodity hardware to the cluster, and you can scale your cluster. It's economical. Your commodity hardware is pretty cheap. You can buy cheaper hardware and add it to your cluster. Your cluster is economical, efficient by distributing your data parallelly and processing it parallelly across different nodes. Your system is efficient, and it's reliable also. So basically, it's not only maintain a single copy of the data, it maintains multiple copies of the same data across different nodes. How that is maintained, I'll talk about that part in some time. So let's make it reliable also. So if some node which has your data which need to be processed or which is required to be read right now is down, you can't read the data. As these are commodity hardwares, it's a high probability that those go down. So your data is divided in blocks and replicated across nodes in the cluster. How that is done, we'll look into that part. So that makes the system reliable. So these are the some assumptions on which this whole ecosystem is created up. So hardware will fail. This is the first assumption which cannot be overcome. So hardware will fail. You can't do anything about it. Application needs write once and read many times. So as you are processing your big data, or your enormous amount of data, it does not make sense to read that data again and again. As practically you will be you will be dumping the data once, and you will be practically reading that data again and again to look at different statistics about the data. Then the next bottleneck in the system is the data transfer across the network, or IOs of the data, or to read or write the data basically. And you are working on very large data sets, and the beauty about the cluster is you move the logic rather than the data. So when your data is divided across the cluster, something like this. So if I have to, okay, I'll look. So if I have to process that data now, I can read that data individually on these nodes. But if I have to process that data, I have to figure out some statistics about the data. I basically, the one way is I can transfer that data from different nodes to my master node. I can do the processing over here. But if I'm doing that, I'm transferring the data across the network, and you can think of the network speed, which will become a bottleneck. And second bottleneck which will become is you're processing your data again on a single node. So what is done is rather than transferring your data to get processed, you transfer the logic, and the logic would not be on more than few bytes or few MB kind of thing. So you transfer your logic to the nodes where your data is lying. So if your data is distributed across these 10 nodes, you will transfer your logic, which will be a few bytes or few MBs, to these nodes. These nodes will be processing the individual data which is lying on these nodes, and will just send the process results to you. So if say I have a data like something like Design Pathshala website, so there I have the say click stream. So if I have to look at what is the different age groups of users who are clicking my website, so I'll just send a logic select from click stream, and group by age group 0 to 21, 20 to 42, and 40 to 63, and just sum up the different counts of these three age groups and send it to me. So from each node I'll just get some counts, and I can later on do a count on total count on them, and can just present the results. So you don't transfer your data, you just transfer your logic of processing the data to the nodes where your data is lying, and that's the beauty of the cluster, and that's the beauty of the whole ecosystem. So if you have to transfer your data, you can think of the bottlenecks, different bottlenecks which can come to you. So it assumes that your hardware will always fail, and it really basically transfer your logic rather than the data. So this is how your whole system looks like. You have your data nodes. So the nodes which contain your data are called data nodes, or the commodity hardware just talking about is basically called the data nodes in the in the architecture. So the green ones over here are the data nodes, which really contains your data, and there's something called name node in the cluster, which is the master of the cluster. So name node maintains all your metadata of the cluster. So the metadata is which data is lying where. So name node knows which data is lying in which data node. And when I have to read some data, I just interact with the name node. Name node tells me where my data is lying, and then I go to that node and read the data.
So it's more like an index.
No, it's not like index. It's just the metadata of your data, where your data is lying. It's not there's no indexing kind of thing which is happening on your data. Name node does contain the pointers to where your data is lying. I will not say it's an index.
Just one question here, like the data nodes can be different kind of databases.
Okay, so there's nothing like that. Okay, so you have to overcome your the concept which you're reading till now. There's nothing like database over here. All you're storing is a file system. So you're putting your data or all your data is lying in your file systems. There's nothing like databases, relational databases, or over here. It's all file system based thing. So we started with file system in 90s. Then there's an era of relational databases came up. Oracle, MicroSQL really, taken up the market. DB2 started with DB2. They really taken up the market, and again now people are moving on to the file system. So all your data is lying onto the file system only. You are reading those files, processing those files, and presenting the results or statistics out of your data. So your data is lying on these nodes, which are green color over here. So previously what I was showing over there. So like these different files related to different things are lying on your data nodes. Like project related thing is lying on some data node, images related thing is lying on some data node, and things like that. And so practically, so things like that are lying on your data nodes, and name node just contain where my data is lying. Does that make sense, Suraj?
Yes.
So isn't it like an index of a book?
It's no,
At the back of the book, you always
okay,
have
but
like
yeah. So,
means I'm not talking
yeah,
about index in the sense
yeah.
of
So
database.
it's like that only. You can say yeah, like at the back of the book.
Yeah. Okay.
Which word is lying here, or which word is occurring on which page?
Correct.
And there's something on secondary name node. So secondary name node is basically okay. So this is architecture of Hadoop 1.x. We'll look into the yarn architecture, which is Hadoop 2.x architecture in our later on classes. This is architecture of 1.x. So there's a little difference between 1.x and 2.x. So there's something on secondary name node in your 1.x architecture, and if your name node goes down, then secondary name nodes keep on interacting with your name node and has the recent history of your name node, so that if your name node goes down, physically the secondary name node can be basically made up, and then your request will come to secondary name node. But in such a scenario, basically there is a manual interaction which is required in Hadoop 1.x architecture, and that really fail this thing. Hardware will always assumption of hardware will always fail. So that really make the system down if your name node goes down. So there are changes in this architecture, and now in the 2.x architecture, this has been taken care with the help of the architecture of the system. I'll talk about that high availability of the system sometime. So second name node is nothing but a copy of your name node, and the name node copy is basically maintained by secondary name node. So in case a name node goes down, the secondary name node is made up, and the request can then be processed by your secondary name node. But if your data node goes down, the same data is replicated somewhere else also. So if this data node goes down, the similar data might be lying over here also or here also. And name node knows about which name node, which data node is up and which data node is down. So it will tell the client from which data node it has to read the data. So single namespace for the entire cluster. So entire cluster maintains a single namespace as I've shown you in the previous example. How the data is replicated, we'll look into that part first, and then I'll come back to this. So I'll come back to these slides. Let's first look at how the data is replicated. Then these things will make sense to you. So let's say this is my cluster, and sorry. So let's say this is my cluster, and right now I'm assuming there is only one data center in my cluster. However, there can be different data centers in a cluster. In this example, we are assuming there is only. So I hope you understand what is rack and what is data center. If you're not, just ping me right away before I go ahead.
Yeah, I know. So it's okay.
Yep, I'm aware of it.
Right. So I'm assuming in this example, in my cluster, there's only one data center, and this is the data center which is displayed on the present slide. So each rack has 4 nodes for 4 machines on them. So let's say there's a file which is of approximately 64 into 5 MB. It need to be stored onto my SDFS file system or onto my Hadoop cluster. So basically what happens is your files are broken into blocks, and the default size in 1.x is 64 MB, in 2.x is 64 into 2, that is 128 MB. So in 2.x is 128 MB by default block size. You can definitely change those things. So basically your data is your files are divided into blocks, and it's the blocks which are placed into the system. So let's say the first block need to place into the system. So that block is placed randomly into any of the data nodes. So it gone to disk 1. The next, so the blocks are replicated in the cluster. So the minimum copy of the blocks is 3. That is the default one also in your ecosystem. You can change them. You can even change it to 1, but that will not give you the in that case your system will not behave like how it's need to behave. So you can change that to 5 also. It's up to it's again configurable, but the default one is 3, and the suggested one is also 3. So minimum 3 copies of the same data is lying in your cluster. Second and third copies are sent to different nodes, and here they go into rack 2. So I just wanted you to think of what could be the logic of them sending to the rack 2 and to different nodes.
2 different nodes just to protect against server failures.
Server failures, and 2 different racks to
protect against rack failure.
So yeah, definitely. So there's a high probability that the whole rack 1 can go down, and similarly there's a high probability that the whole disk 1 can go down. But the probability of 2 racks going down in your data center is less as compared to 1 rack going down. So here we are trying to minimize the risk as much as possible. Definitely the 2 racks can go down, but the probability of them going down at the same time is pretty less. So we try to divide the same block across different nodes so that the probability of some hardware going down, if there's basically some hardware goes down, that could be that data can be read from somewhere else. So the second question is, why do you think the third copy of this block is not placed on rack 3? It just the second copy and the third copy of the same data is placed on rack 2. Any guesses?
Speed.
Speed in terms of?
In terms of you don't have to go across the racks. Then means if you go across the racks, then after the speed at which you will write, because you'll have to go through the switches for the racks. Right?
Yes. So the data transfer, yeah, definitely. The data transfer speed between one rack to another is much less as compared to data transfer speed between the nodes inside the rack. So if I have to transfer this data across the NAC, and then again there's a network bottleneck which will come in picture. So to reduce that part, the third copy is placed in the same rack. So basically the algorithm which is used to place your blocks, the default algorithm which is used to place your blocks, is the first copy is placed on randomly on any of the data nodes across your any of the racks. Second and third copy is copied into a different rack from where the first copy was placed, but the second and third copy are placed on the same rack.
Does the algorithm take care of placing the copies on racks with minimal amount of data or minimal amount of current usage?
So there are different things which come in picture if the data node is processing some, if the data node has the bandwidth to copy the data, and how much data is there. These kind of things are by default there in the algorithm, but definitely it's configurable. You can change these things by configuring the algorithm.
No, in the sense just to avoid hotspots.
Yeah, definitely. Everything is taken care at the back end to avoid hotspots, also to avoid. So if there were more than 2 data centers, that would have taken care of the data centers also.
This is not actually like a kind of like a recovery scenario, right? Because if the processing of the data is going to happen, so it will be happening from all the 2 racks, right? For all
No. So if just give me a minute, I'll answer also. Just give me a minute. So that was Suraj, right? So just give me a minute, I'll answer your question. So let's say the second block now need to be placed. So any guesses where it go? Suraj, I'll answer your question in 5 minutes. Any guesses where it go?
Again, it would be random.
Randomly, yeah. And the second and third copy?
maybe on rack 3.
That's not
1 or 3.
Yeah,
1 or 3.
That's the perfect answer, 1 or 3. So it can go to any of the racks and any of the nodes on those racks. So it's gone to rack 1, say. And similarly for the other blocks. So it came randomly onto testnet, and the next 2 copies would go randomly on other node, not rack 2. So to answer your question, Suraj, what happens is basically when you have to process this file. Now I know where are my blocks of the file are lying up. So and and with the beauty of the ecosystem, how that beauty is achieved, we'll look into that part. With the beauty of the ecosystem, I know which data node is free. So if say disk 1 is free, I'll send my logic to disk 1 that process the block 1. Then I'll send the logic to disk 2 to process the block 2, and then I'll send the logic to disk 10 to process the block 3. And they will process the blocks and will send the results to me. I will not be sending my logic to disk 6 and disk 7 and disk 8 in this scenario. So, and although they have the block, the copy of my block, but it does not make sense to process the same block again and again on different data nodes. So we process the block only on one disk, and it's on the basically on the availability of the disk. So if this disk is doing some work and there's no RAM and processing power free on this disk, in that case my processing request can go to disk 6 also. So you send a processing request to your disk based on the availability of those data nodes and how much bandwidth they have, and the data is processed locally on those nodes, and it's the process results which are sent to you.
Okay, I'm able to get that, but like my question is like why we need to have the data like 1 and in this 6 and 7, because anyways at a given point of time we'll be processing it from one block, right? Like one disk.
Yes.
So
Okay. Okay. That's a good question. So 2 things. One thing is hardware can always fail. So it has to make the system reliable. The property about the ecosystem is, the system has to be reliable. Now, if your disk 1 is down, or disk 1, the whole rack 1 is down, you are lost with your data. First thing. So to make that reliable, your data is copied at least thrice. So it will be difficult for you to understand this, concept, or basically, digest this concept, basically, not understand, digest this concept, because till now you were looking at the relational databases, where the replication and normalization was good enough, was good things. But now we are talking about the systems like this, and where normalization really kills the system. Replication is the available thing. Hard disk is the cheapest thing now in the world. So those systems were created assuming hard disk is costly and things like that. But the days are gone. Hard disk is pretty cheap. And the second thing is, now if say I have only one copy of the of block one. Now if this block need to be processed up, and this disk is busy in processing some other blocks which are also lying on this disk, so it's not only the one block which is lying on this disk. There'll be other hundreds of blocks which are lying on this disk. So if this is busy in processing some other blocks, I have to wait till the processes are over and then give the request to process this block one. But if my block is replicated to disk 6 and disk 7 also, I can easily send the processing request to disk 6 or disk 7, whomsoever is free. At a time, all the three nodes busy, in that case I have to wait, but the probability of all the three nodes busy at the same time is pretty less, if you are not basically running a pretty huge processing on your cluster. So to reduce or write contingencies and read contingencies kind of things also, the data is replicated across the cluster.
Okay, so now again you're okay. So now I believe you are going back to the point like where you can send your logic onto disk 6 and disk 7 also, right?
Yes.
Because I heard, yeah, because you initially said like, no, it is always one. So I was a little confused with that part.
Oh, okay.
Okay,
So
now,
this was just an example which I gave. Okay.
oh yeah, actually that's what like the statements come bit in contradictory. That's why I was asking you.
Okay. So logic can go to any of the nodes which were having a copy of the block. So that was just an example just trying to say it can go to disk one, and the second logic can go to disk two and so on. But it can definitely go to disk 7 or 6 also for block one.
Yeah, but that again contradict one of your again statement is like if you're processing from disk one, why you wanted to process the same thing again from disk 6 and disk 7?
Sorry. Let me rephrase what I'm saying. What I'm saying is you can send your logic which need to process these 5 blocks of this file. That logic will go to 5 different nodes, or that logic can go to less than 5 nodes also. In such a scenario, that logic can go to this disk also, where it can process the block 1 and block 2. So the logic can go to any of the nodes where your blocks are lying up, but that logic will be sent to process your block one block at once only. It will not be processing your one block at two different data nodes.
Okay.
I think this is very similar to even the last few years in the relational databases also, like Oracle. If
Yeah,
you are
they have
using
multiple node clusters.
So
no, no,
MPP
no. If you are using say AMS, automatic memory management, right? So in which case there is something called as normal redundancy, and also yeah, there is some mirroring of the blocks across different disk groups, which is very similar to this, where you protect against failures and provide high availability.
yeah.
So it's a concept
So
which is there in RDBs also.
yeah, this concept is would be available in different flavors. But the next thing comes up how you process the data. So you can process your over there. What will happen is again you would be having you would be mirroring your data up to, in two different servers where you have to vertically scale the servers to do the processing. Here I am doing horizontally scaling of my whole cluster on smaller data nodes. And there is something called trackers of the system dot tracker and task tracker which you're looking at. So they really maintain which node is free. So you can parallelly process your data, but over there where you can distribute your data, but you will be practically having vertical servers of high availability kind of servers, and you are just parallel distributing a request to one or two or five different vertically scaled servers or pretty high processing power servers.
Yep.
So, okay, so this is what I was saying. Single namespace of the whole cluster. So you can interact with the cluster with a single namespace, and you have to just say your file name. Your name node knows where your data is lying up, and your data is divided into blocks. So name node now that will make sense to you. So that's the reason I was not saying it's indexed. So the name node just knows which block is lying where. So a file has 10 blocks, and these 10 blocks are lying at so and so data nodes. So this is the kind of metadata which name nodes contains. So
That's like this design algorithm which you explained, like that comes with the system, like we have to define that, or
no,
is
no,
that
no,
something?
it's already configured. You don't have to define anything, but definitely you can. If you want to change it, you can change it. So
Okay.
it's all open source. Everything is configurable in this world. You can change anything, but there's a default one which is there, which Hadoop comes with it.
Okay. Thank you.
So So your files are broken into blocks, 64 MB and 128 MB for 2.x architecture, and the blocks are replicated across your data nodes. Write once, read many times. That is what I've already talked about. And clients are intelligent, so they know where your blocks are lying up with the beauty of the ecosystem. That is the name node. Right. So before moving into the Hadoop ecosystem, you have to think of if the solution is not really a kill for yourself. So people are just blindly trying to just to market themselves, blindly trying to move on to Hadoop or uh, similar kind of systems. But they have to really think of does it really make sense to move them to the Hadoop ecosystem, or just an overkill to the solution. So this is a graph which is trying to display. So don't I do not claim any of these figures. So this conceptual picture where I'm trying to tell you how you can think of if the solution is really not an overkill to you. So the graph in the traditional databases is something like this. When the data is less, the processing time is very less, in less than microseconds or less than seconds. But as soon as your data grows up, your graph is almost vertical. In the Hadoop ecosystem, your graph starts from somewhere here. So there's an initial time which is always required to start up your process, and there's a lot of metadata handling and a lot of things which happen at the backend, which we're talking about. And your graph for as soon as your data increases is almost horizontal. It's not a vertical kind of thing. So you have to think of where your intersection is happening up, and at what kind of data you have to really move on to the ecosystem like Hadoop. If you are moving to Hadoop ecosystem and you have only this kind of data, you are really overkilling your system, or your solution is really overkill to you. So you have to think of if you have to really move on to these systems, or is just the vertical scaling of your current system can handle your data.
Isn't one of the advantages of Hadoop or maybe other NoSQL kind of databases that it can handle unstructured data, which
Yeah.
traditional database doesn't like, independent of the size of the data, right?
Yeah. So Hadoop as it's storing your data in the file system, so you can definitely store your unstructured data, and uh, so there are things like what we call that blobs and things like that is there. But definitely, yeah. If you have to, that's what I'm saying. It's not only the data size. Sometimes to process that unstructured data, you require a lot of processing power. So this intersection will come somewhere here itself. So in such scenarios, so that is the point which I'm trying to make over here. So based on your data size, not only the data. So what I'm saying is, it's not only the data size which is required to process, so which takes more time to process. It's the complexity of the processing power which is required to process your data. So how much that complexity of processing power is required, you can think of how much you have, and at what time you have to move on to the Hadoop ecosystem. So
Okay. Yeah.
the data might be big, even a smaller data might be big data problem for you, based on the complexity of the processing power which you require to process that data.
Yep.
And yeah, definitely NoSQL is a totally different world where you can have your totally unstructured data. You can keep on creating columns on the fly. So that's totally a different world. So, but here you can put all your unstructured data definitely. So these are the different flavors of Hadoop which are available in the market. So Hortonworks have their Hortonworks Cloudera MapR are totally open source. Provotal and IBM are proprietary. Hortonworks is 100% open source version of Hadoop, totally aligned to Apache open source, and Cloudera is also open source, but they have few proprietary components like Impala. Um, uh, MapR is again a flavor. So these are different vendors who basically uh, uh, change little things on the open source version of Apache or Hadoop, and basically package everything and then distribute these things. So these are different distribution vendors for the Hadoop ecosystem, and these are proprietary ones also. So we'll be looking at Hortonworks one, but the code, the things which you are looking at, how the processing is happening, all the ecosystem is everything same because they are all implementing Apache open source. So nothing will change if you want to use Cloudera or MapR or any other thing. But in this whole classes and our all the classes will be looking at the Hortonworks VM. So, but if you want to use any other thing, you can definitely use them. Nothing will change. Everything is the same. The components might change here or there, or there will be some extra components will be available in different versions or some less. But the code and the processing and everything will remain same.
In terms of install base, which one is the highest install base?
Hortonworks and Cloudera are the two mostly used in the industry. Different people have different opinions. So I cannot really comment on any of these things, but these are the two highly used in the industry.
Even on like bigger enterprises like eBay, like top companies also they use Hortonworks.
I don't have the inner information. But for if I work for eBay, they were using Hortonworks. It depends on the organizations also, but Hortonworks and Cloudera are the widely used across the industry.
Okay.
And the difference being the administrative tools, or because the basic Hadoop is going to be implementation is going to
Yeah,
be same, right?
it's how the different ecosystems are interacting, how the different components are interacting with each other. That might be a difference, or if they can basically add on different things, or reduce on different things, or how the administration work is happening at the back end. But for the developer perspective, it's exactly same to us.
Oh, okay.
Like I told you, Cloudera has something called Impala. So Impala gives you a in-memory SQL kind of thing. Then MapR has things like Green Plump and things like that. So the few differences in these things, but as the developer perspective, it's all same to us because the processing or the code which you are looking at, how we are putting up the things, it's all same.
Okay.
So there are a few pros and cons which are highlighted over here also. Any other questions?
And the hands-on that we will be having with the session will be on Hortonworks.
Hortonworks, yeah. What I'll be sharing with you is the Hortonworks, but you can definitely try it on different flavors. So if you want, it's all same.
Oh, thank you.
Okay. So. Okay, so block placement strategy, which I've already discussed in the previous slide. That is this one. So one replica on local node. So why local node? Because I can reduce the transfer time of the block. So a client when client is giving a write request, he or she might be setting up in any of the data nodes on the cluster. So the first copy is basically based on the local node. That is the default one if the local node is free. Otherwise, it might go to somewhere else. Second and third one will go to a remote rack, and additional will randomly be placed on a different racks.
And if you got a multi-locational
Data
cluster,
center.
data
Yeah.
means multiple data
Data
centers,
center.
and the
So
cluster is spanning across data centers, then can you force the second copy to go into different data center?
yeah, in the default one, it will go to the different data center. But again, you can configure these things. So you can change your algorithm, and you can think of where you want to put your data. Or basically,
And then,
if you're
yeah,
having
go ahead.
multiple data centers, so practically three will not be your replication factor will not be three. You would like to have it increased to five or something like that.
Yeah, and then while reading or while processing the data, can you force preference on where it reads from? Because reading
Yep.
from a local block or
Yep.
local server will always be faster, right?
That's what I'm highlighting on the screen.
Oh, okay, okay, perfect.
So the beauty of the cluster is your name node knows where you're setting up. So when I asked to the name node, I want to read this file. Name node knows where you're setting up, and name node also knows which are the data nodes which have the copy of my data. So it will return you the nodes which are nearest to me.
Oh, okay, yeah, okay.
So the name node maintains the metadata. The metadata is not only the files or the blocks about the file, but also which about the data node, which data node is up, which data node is down, and things like that also.
Yeah.
So again, the same thing replicated on this slide, but now everything will make sense to you. Any questions?
No.
Okay.
Not really.
Right. Okay.
For
So
replication, how does it handle missed communication between the nodes?
okay. So
Or if we are going to cover later, then I will
yeah,
let you.
so I'll cover it over here.
Yeah, no, don't worry. You don't have to jump around. Yeah,
Okay.
I'll just ask questions when they come to the mind, but you can feel free to say I'll cover later.
Okay, actually, yeah, definitely. But you can just write down a question so that you can recall them when I'm discussing the same topic.
Yeah, I'll put it in the chat.
Yeah. So okay, before moving to the architecture part, any other questions? Sorry. Okay,
Not as
so
of now.
okay, so we can just take a quick 5 minutes break and we can start in next 5 minutes. Is it fine?
Mm-hmm.
Sure. So we'll just meet in next 5 minutes and then we'll start on the next. Hi, I'm back.
I'm
You're
back
there?
to
Uh,
yeah, Miraj.
just wait for Mahesh also.
Yes, yes. Hey, Miraj,
Yeah,
I would like you to ask you something. like, I'm going to India on 15th of July, okay, for 2 weeks.
15th of July. 15th of July. Okay. And today is
So,
27th. Okay. Yeah.
so I was little wondering, like, I was talking to the administrators of Design Pathshala,
Mm-hmm.
and they said to discuss with you if something can be doable during that time.
Okay.
So,
So,
so we can talk it later also. I'm just giving you a heads up. Let me know, like, if you can help me out.
okay. So what we can do is once Mahesh is there, we can just discuss it. If you are okay with some of the classes on the weekdays, we can try to figure it out and we can try to wind it up before that.
Sure, sure, sure.
So if you are okay with the on the similar time on the weekdays or somewhat earlier or later on, that works for me. I am right now free in the mornings of my weekdays, so we can take out some classes and we can definitely try to because it normally takes 4.5 weeks, so it will be just 2 or 3 classes. So we can take 1 week, 1 weekday, 2 3 weekday classes, and we can definitely do that.
No problem. Yeah, we can work on that. Thanks about it.
So as this batch is not big, normally it's 5 or 6 size, but I think this batch is just 2. So we can definitely take care of the thing.
Okay, sure. So, like, one more question though, like, until like Mahesh comes in. Say, for example, like, a company has a data in the traditional database format,
Mhm.
and they wanted to do some sort of like a research or analysis or something.
Mhm.
So, if they need to read the data, so then again they need to convert that in the file systems, and then they need to do the analysis using the Hadoop, right?
So practically what is happening up is this relational data is getting moved into the Hadoop related systems, and thereon once the data is written up, but that data is used for different analytics. So all the analytics is basically running on these kind of systems. Your still the
Okay.
transaction related stuff is not yet moved on to, although people have started moving the thing, but that is not moved on at a pretty great rate. The transaction are still happening in your relational worlds, but the analytics and other thing is happening into the Hadoop related things.
Okay. And like actually like in Hadoop, like as you said, like the data can be like the most important reason like why people they're using Hadoop is like because to do the analysis and to do the processing of the unstructured data, correct? Now, so so if some like if we are trying to read some data from relational database, which assumable like is having a whole lot of like structured data, so that it will be easy for Hadoop like to do the analytics on top of it, right? To do the like
Yeah,
so I,
definitely not just the structured data or unstructured data. It's a structured data which is also there because most of the data which is getting it moved onto this system, other than the IoT, is coming from your relational world only.
okay,
So that data is now used to fire. So now people are setting up with people are setting up with enormous amount of data which is collated in their data warehouses. Now that data is getting moved on to that data is merged and married with your unstructured data also, which is coming from different sources, and people are using that whole blend of data lake to come up with different analytics on the data. So the different analytics which are talking about previously, so that analytics cannot be just gathered from a single source of the data. The data is coming from different streams. The data is coming from their Facebook posts, Facebook data is coming from their Twitter account, data is coming from their LinkedIn accounts, data is coming from their Clickstream account, data is coming from their Google Analytics account, data is coming from their uh, real order, that is the transactional data is coming from their server logs. When they merge and marry these things, then only they come up with these analytics which I was talking in the previous slides.
okay,
Hey Mahesh, are you back?
Yeah, yeah, I'm there.
Okay. So this is the architecture which we looked into. Now here I'm just talking about the name node. So So the name node contains your metadata, that is which file, so how much what is the replication factor, how many blocks are there for each file, where are those blocks lying up and things like that. And when I have to read it, I just request the name node. Name node returns me the metadata, that is where my data is lying, and it also takes us to return me the nearest nodes, and then I read on from those nodes. And when I have to write, name node returns me where to write. I as a client send a write request to those data nodes. There's a whole write architecture. I'll talk about that write architecture in the next slides. So now everything we have discussed, all these things, but I'll just quickly reiterate them. So name node contains the metadata in memory, the list of files, the blocks which are associated to the file, list of data nodes for each block, the file attributes like creation time, replication factor, deletion time, and things like that, and the transaction log like when the file was deleted or created and things like that. So this is the whole metadata.
When you say metadata in memory, that means does it cache the metadata to begin with?
Oh, no, and that is not the caching part. It is memory, that is whatever is stored over there, not in terms of caching.
So when you say memory, it is storage actually.
It is storing also, but most of the data is there in the. So this is based on the infrastructure of your again on name node, how you have configured the name node. If name node has a good enough RAM, it might be caching up your, but everything is persisted also.
Okay. So if it is in the memory, then is there something similar to the checkpointing? So at a given
checkpoints also.
In the sense, given frequency, it will be flushed out to the disks on that node, particular node.
So the basically okay, let's look at this HA. I'll come to your question. Just give me 2 minutes. Let's look at how this HA happens, and let me come back to your answer. I think some of the things might be answered over here.
Okay.
So basically, what happens in 2.s architecture? What happens is there's something called secondary node, and there's something called secondary node, and that nodes keep to copy the name node. But what happens in 2.s architecture is that is high availability architecture. So there's two separate machines called name nodes. One is active at a time, another is passive at a time. So one node is active and another one is standby at a time. So active node is responsible for all the client requests which are coming to the cluster. So the active node handles all the requests which are coming to the cluster. In order to keep your standby node synchronized with your active node, there's a communication which happens within both the nodes, and that happens with the daemon threads called general nodes. So whenever there is some modification happens on the active node, the logs, the chain logs or the modification logs are sent to these daemon threads from where the secondary name node keeps on reading it. Secondary name node basically reads these general nodes and constantly watch for any of the changes which are happening on your name node, and basically read those edit logs and keep on changing the state. Now, in case of any failure which happens on your name node, the standby nodes ensure that it has read all the things which are there, which are being added to your edit logs, and once everything has been read, then the standby nodes becomes active. In case of this active node, there is some failure on the active node, and everything is managed with the help of Zookeeper, which is running in the cluster. And in order to provide fast failovers, it's not only the edit logs which are maintained by your secondary name node, but the data nodes also keep on sending the heartbeat signals to your name node, so that name node knows the data node is up and things like that. So these data nodes not only send the heartbeat signals to your active node, they also keep on sending the heartbeat signals to your secondary nodes, so that when the secondary node has to be made up, it knows the current structure system which data nodes are up. So the change logs as well as the data nodes which are up, everything is known by the secondary name node. So it's pretty easy, or it's almost transparent to the user to make the secondary node up. So now to your question, that data is kept in memory. So the change logs keep on persisted to the machine as well as they keep on going to the general nodes. So these chain nodes are maintained by your name node. Something might be in the memory or it might be flushed down at the time. I have to cross check that part, but this is how it happens at the cluster level. So the change, the things which are coming right now would be definitely in the memory, but how that is flushed to the disk, that I can cross check that part and come back to you.
Okay. Yeah, because that is what I was looking for, is what frequency it actually flushes it out to the disk so that it goes to the standby node, right? But there is a connected. You talked about heartbeat signal from the data nodes to the name node, right?
Yeah. So this heartbeat signals tells about that the data node is up. Secondly, there's a checksum which runs at the backend, which name nodes keep on triggering on the data node. So that basically checks the blocks which are lying on the data nodes are not corrupted. So if the blocks are corrupted, then the name nodes give a signal to some other data nodes which have the copy of that block need to be copied to some other block, so that the replication factor of 3 is maintained in the cluster.
And the question was slightly different, that network connection drop or network loss of connectivity is not very uncommon, right?
Yeah.
Now, if there is a momentary loss of connectivity from data node to the name name node, the primary name node, how does it know that that particular node is down? So let's start communicating with standby, because there are only two, right? So if one data node, there are 10 data nodes, how do they really know that the primary name node has gone down?
So first thing, data node do not have to know the name node is up or not. They will just keep on sending the signals to the name node. Second thing is, if there is a connection problem between the name node and some of the data node, and the name node is not able to get the heartbeat signal from the data node at the predefined frequency, name node will safely assume that the data node is down. And in such a scenario, if the name node has got to know the data node is down, it will send a signal to other data nodes which are up and which have the copy of the blocks which are maintained by that data node to re-replicate those blocks so that the replication sector in the system is maintained.
No, I understand that, but what you are talking about is loss of communication from name node to the data node and data node going down.
Yeah.
What happens if the primary name node actually is not down, but there is a loss of communication because the network could be a problem?
Yeah. So yeah, there's something called Zookeeper which really maintains your cluster, and this is your active node, this is your passive node. Right. So if there's some problem in the network, Zookeeper knows that active node cannot be communicated right now. So in such a scenario, it will make it as a passive and it will make it as an active. So once it's made to active, it will ensure that all the commit logs which are done from the active node are being read by this passive node, and then only this passive node will be made active. And in such a scenario, the write request from the active node will be, so that in that scenario, what will happen is the active node will not be the write requests to the general daemon process which are running at the backend will be taken up from the active node, and the passive node will get the write request, and the active node will just have the read request from those general node. So active node will not be able to make any changes in the metadata.
So this Zookeeper is another node?
Zookeeper is a separate process which is running in a cluster, which is really managing all the processes which are running in a cluster.
No, but is it running on a separate node?
So it can run on a separate node. Practically, it should run on a separate node. So your cluster. So there's something called name node, the data nodes. Then the Zookeeper might be running on your some node which is at good configuration, which is managing your whole cluster. It's not mandated to run on the name node, but it can run on the name node also in a smaller cluster. So in such a scenario, you might face different issues like the Zookeeper node is down and things like that.
So the Zookeeper becomes the single point of failure then. Okay.
Actually, that's not a single point of failure. How that happens is okay. I'll get a picture of this thing and I will explain to you.
Okay, no problem. No problem. I can wait.
So I'll show you in the picture, that will make more sense. But that is not a single point of failure, definitely.
Okay. All right.
So I'll write it down. Tomorrow I'll show you that. Okay. So data nodes, as I shown you, as I told you, they keep on sending the heartbeat signals, and they can store the real data, and periodically keeps on sending the heartbeat signals also, and facilitate the data write pipeline. Okay. So now let's look at how the data is really processed into the system. So this till now we were talking about how the system looks like, what are the different components of the system. There's something on name node, there's something on data nodes. To make it system to make this to basically remove the single point of failure of the name node, there's something called active and passive state in the yarn architecture, and then so this is the whole system, and how the different processes are running the system, and how they are helping you to do the parallel processing. Now let's look at that part. Any other questions rather than the other than the zookeeper part from anyone else?
Not yet.
Okay. So there's something called task tracker, and there's something called job tracker in the system, which really do a processing of your data. So in this picture, although task tracker, you can see it's running on the name node, but practically task tracker can run any of the nodes, but that node should have a good infrastructure to run that job tracker. Not the task tracker. Sorry, job tracker. So in this picture, you can see the job tracker is running on the name node, but in a bigger cluster that can run on a separate node where different from the name node. But practically the job tracker is maintaining a basically is master of keeping the tracks of different jobs which are running in the cluster. So it makes sense for you to run a task tracker on the node which has a good which is not a commodity hardware again. So that's the reason in this picture it's showing it's been shown it's running on the name node. And task trackers are the real workers which really process your data. So the job tracker just manages the processing in the cluster. So any request of processing the data goes to your task job tracker. Job tracker then distribute that request to the task trackers on the data nodes, and those task trackers really run the request of processing the data on the data nodes. How that happens, we'll look into the different in the next slides. But the job tracker is your main process which monitors all the processing requests which are coming to the cluster, and those goes to your task tracker. Those are basically delegated to your task tracker, which really has your data. So and the task tracker really run your mapper and reducer code to process your data. Now here again the point comes to it, the job tracker is a single point of failure. If the job tracker is down, the whole the person who was really managing your whole cluster is down. Sorry, not managing, but basically executing the different processing of the cluster is down. So this is again overcome in the yarn architecture. How that happens, I'll show you in the yarn session. So there is nothing called job tracker and the task tracker in the yarn architecture. But if you understand this concept, understanding the latest concept will not take more than 5-10 minutes for you. So just understand this concept, and the similar concept is there in the yarn architecture, but the dependency on a single process is not there in the yarn architecture. So I as a user submit the job to job submitter. Job submitter gets an UID from your job tracker. This is the job tracker which is running in the which was running on the same name node. From this ID, I'll be tracking my job. Then basically we compute the splits till tomorrow. Just assume the split is nothing but a block. That is a block in which your data is divided. So if your file has 5 blocks, it will just compute how many blocks are there in my distributed file system for the data which need to be processed up. Although the split is little different from a block, but for till tomorrow, just assume the split is equivalent to the block. Based on the computation of input splits, how many input splits are there? We copy the job, basically the logic to the distributed file system, and we submit the job. So now with the logic that the jar which you have created is submitted to is basically kept into a distributed file system, and we just submit the job to the job tracker. And we also know how many split or how many blocks are there which need to be processed up because if my file is divided into 5 blocks, I have to process it at 5 different data nodes, things like that. So once the submit request is given to your job tracker, it puts the job into the job queue, and then the jobs are basically picked from the job queue, and your mappers and reducers are created for the job. And these mappers and reducers are really running with the help of your task tracker. So these before going to that part, I'll reiterate everything. It's a little fast which I'm going up, but I'm just trying to give you the whole picture, then I'll reiterate everything. So these task trackers keep on sending the heartbeat signal to the job tracker as the data node sends the heartbeat signal to the name node. These heartbeat signal tells how much capacity the task tracker has, the previous jobs which are assigned to those task tracker, what is the state of those jobs, and things like that. So based on the availability of the bandwidth on the task tracker, job trackers picks the tasks which are placed in the queue and assign those tasks to the job tracker. And now in this picture, the job tracker is down, the task tracker is up as compared to the previous picture. And so based on the heartbeat signal which have been sent to the job tracker, the jobs are assigned. The tasks for the jobs are assigned to the task tracker, and the task tracker reads the data from the logic from the digital file system and process that logic onto the local node. So I've gone everything very fast, but I just wanted to give you a picture, and I'll reiterate everything. So in total, what I'm saying is there's something called job tracker, JT, and there are different task trackers, TTs, which are running on your data nodes. These task trackers keep on sending the heartbeat signals to a job tracker. So in such by that way, job tracker not only knows what is the state of the data node, how much bandwidth is available to take furthermore requests to process. It also knows what is the state of the previous tasks which have been assigned to that data node. What is the state of that? If something is failed over there or things like that. So a job is divided into different individual tasks, and each task is processing one block at a time. Because on a data node, it's only the one block which is lying up, or there could be different blocks for the same file. In such a scenario, 2 requests will be going to that data node. If there are 2 blocks which need to be processed on the same data node, there will be 2 tasks which will be initiating on that data node. So there will be 2 requests for initiating the task which will go to the task tracker. So I'll repeat again. I submit the job, I get a job ID from the task tracker, and then the split information is being computed from the distributed file system, and the resources which are required to process your data, that is your logic, is copied into the distributed file system.
Can you go back? Yeah. Which process does this split?
Which process does this split? So there's no split. So we just compute the number of blocks which are associated to the file. So
which process? I mean, job tracker does it or task tracker does it?
A job tracker. So this is all everything happening on the job tracker node only.
Oh, okay. Okay.
We as a user just submit the logic to the distributed file system. So I as a user basically give the request to submit the job. Once the job is submitted, I as a user just basically give the logic which is really placed into the distributed file system.
Okay.
Right. Once your logic is there in the distributed file system, and the job is basically placed in the queue based on the ID returned to you. You read the logic from the distributed file system, and based on that, mappers and reducers are basically created. And how those mappers and reducers are created? Those are created something like this. So your job tracker divides the task based on the input split which is calculated for your whole data, and based on the input split calculation, that your task is divided, the whole job is divided into individual tasks, and those tasks are assigned to the individual task trackers which are running on the data nodes. And how those are picked up? Based on the heartbeat signal which these task trackers keep on sending to the job tracker, and these heartbeat signals tells how much bandwidth they have to process your new data. And if say the job tracker, if say one job has come up which requires to process a file which has say two blocks, one block and two block, so there are two task trackers TT which are running up, and this is your data node 1, this is your data node 2, and this is your data node 1. So in that case, the request will go to this node and the request will go to this node. Now let's say this task tracker is not able to send a heartbeat signal to job tracker in the predefined frequency. So job tracker will assume safely that that data node or that task tracker has gone down. Now because block 1 was getting processed on this data by this task tracker, now job tracker has to complete the whole job and it's not able to get the heartbeat signal from this task tracker. So it will assume that the task tracker is down. It will assign the task to some other data node which has the same block P1, and then that data node will process that your block. So this is how the replication helps us to process the same data if we are not able to process it somewhere, or if something happens with the cluster or with the hardware.
Just one question. The data nodes are like the place where we have the data, right, for the
Yes.
processing.
Yes.
So like if the data on the D task tracker, like on the D1 is down, the data node 1 is down, then like the data will be copied to some other node, right? Data node.
So okay, two things. One is maintaining the replication factor of the cluster 3. That will be taken care by the name node.
Okay.
How to process the data? So job tracker now knows your blocks are lying on so and so data nodes because the name node has the metadata. So job tracker gets the metadata information from your name node and now knows where are the blocks lying or how many blocks are there for the file. Based on that, now it knows, okay, based on that, now it knows on which data nodes it can start the process to really process your data. And
Okay.
which data nodes need to be picked based on this mechanism. Data nodes keep on sending, task trackers which are running on the data nodes keep on sending the heartbeat signal. They send how much bandwidth they have to start the new process.
Okay, got it. Yes.
And so once your task tracker basically reads the logic which need to be processed, so that logic need to be read from the distributed file system because that logic we are placed in a distributed file system only. So task tracker node, basically the data node reads that logic and run that logic into the separate JVM. The task tracker is running a separate JVM, job tracker is running a separate JVM. The logic which is required to process the data starts in a separate JVM. Any guesses why?
No, can you repeat the question?
Okay. So the task tracker is running a separate JVM on the data node. The job tracker is running a separate JVM on the name node or wherever it's running up. But when you have to process your data, so a separate JVM instance which is initiated for that particular block, and that block is processed in that particular JVM only. So if there are four processes which are running on a data node, so say this is a data node X. So if there are four processes which are running on this data node, there are 4 JVM instances which are really running on this data node, including the one of task tracker. So total 5.
And that could be because those 4 blocks which are being read in those 4 JVMs are for 4 different jobs.
Agreed, but we can do it in the same JVM also.
No, because like you can continue from the JVM, so the JVM can be copied over in case the data from X is like down or something, heartbeat is down. You can read the data like whatever.
No, but Dave, sorry, I not able to get the point which you're making.
No, maybe you can use the same JVM over there. You can migrate the JVM.
Migrate in like?
Migrate means like you can move the. No, I was wrong.
So the simple logic is if while processing the data, there's some exceptions, some errors, and the whole JVM goes down, my task tracker really does not go down, and the other processes which are really running are not affected. So that's the whole reason why it's starting a separate JVM. So each processing which happens on the individual data node by the help of task tracker is basically happens in a separate JVM.
Yep. Thank you about this.
Okay. So and the replication factor of this this thing uh, the logic which is copied into the receiver file system is not 3, is high as 10. Any guesses?
Sorry, what is that question?
Okay. The replication factor of this logic which is copied into the receiver file system, that is a jar which contains your logic, is not by default 3 of the receiver file system. There is a separate replication factor which is maintained for this logic itself, that is maintained as 10 by default. Any guesses? So why I'm
That
asking
maybe
these questions is just to make you rethink about the whole process and come up with all the questions which you have. That's the reason I'm asking you these questions.
yeah, because the logic is being used for accessing parallelly multiple blocks, right? For one block, there are 3 replicated blocks, but you are going to read multiple blocks in parallel, right? So obviously it cannot be only 3 because 3 is for one single block.
No, no, no. So
Where,
logic, no, no. Okay. So yeah, that's the reason I'm keeping on asking. So what I'm saying is the logic has been read from distributed file system, and that logic is initiated in a separate JVM process which starts up, which really works on that logic. So if the logic is written for I equals 1 to 10 do something on the data, so that logic is initiated as a Java process over here and has been ran. So 10 copies does not make really basically it stops me to running more than 10 processes. It's just a copy of the logic. That is a real Java code. If I say in the wrong terms.
but then why is it there is a replication factor of 10 for that
Yeah,
code?
that's what I'm question. That's my question is. I just really wanted you to be able to think of different things which comes to your mind, so that the different questions are clear about the whole algorithm.
So I can only think of protection against failure, but that doesn't answer why it should be 10 instead of
Yeah.
2, 3.
Yeah. So the thing is, the logic is running on the data nodes, and the replication factor of the logic is 10. Now there is no probability that the logic might be up the block the logic might be really lying on the data node on which I want to really start the process. So there is high probability on the big cluster that the logic might be transferring over the network, so that data nodes can read that logic and can basically initiate that logic. So to maintain or reduce the processing time while the real processing is starting up, we maintain the high availability of that logic so that different data nodes can read that logic from the nearby data nodes. Because that logic really need to transfer the network while processing.
Correct.
The data is lying locally, but the logic really need to travel the network.
Yes. So the data node where the block is sitting, it doesn't have that logic, then it is going to read it from the nearby node.
Yes, of course. So because again that is present at DFS only, distributed file system.
Yeah. Yeah, makes sense.
Any questions? Anything?
No, the question is like why 10 copies? Like it should be like available, like you can send the logic over the network, right? So whichever data nodes read this logic, they can have it. I'm little lost here.
Yeah, no worries.
So this number 10.
Yeah. I as a user, I need to submit the job. Why I'm saying submit job, I have to just submit some logic which need to run on my data. Okay. So what I'll say, on this data, run so and so logic. I as a user do not know if my file is 100 GBs or 500 GBs or it has 5 million blocks or 60 million blocks. I will just copy my logic to SDFS.
Okay.
And tell job tracker trigger it please. Now, I as a user cannot send that logic to individual data nodes. I can just copy the logic in somewhere, like when you trigger your C++ code or Java code. What you do? You just trigger your jar. before that you copy your jar into your Unix file system or Windows file system.
Yes.
So I put my jar into distributed file system and I am triggering it. Now that jar is lying in the whole cluster. So if my cluster is something like so if this is my cluster and my logic replication factor was 3, so this is one block where my logic, so logic is always very small, so just assume it's of size of one block for time being. So on this data node my logic is there, on this data node my logic is there, and on say this data node my logic is there. Now when the processing request goes to this disk 9 to process my data, because the block of one block of my file was lying on disk 9, I need to read that logic either from 5, 8 or 1, any one of them. So there is a high time which is wasted just to read that block. So to make it highly available nearby, we have the replication factor of the logic higher as compared to data. So why 10? You can change it to 5 also, but this is the default one. But what I wanted you to think is how the logic is really traversing and how the data is really read.
Okay, got it.
Someone
So
else?
depending on the size of the cluster, you have to really configure how many, what is the level of replication, right? Means if you got a small cluster, even a replication level of 5 could be enough. Or if it is a real large cluster, you could decide to have a replication logic of the order more than 10 also.
Yeah, definitely. These are default one which are there. I'm just talking about the default ones. You can definitely everything is changing. So in our development cluster, in one of my development cluster, we have just 5 nodes, and we have enormous amount of data. So sometimes we have to make the replication factor 1 also to just test out our codes. We just make the replication factor 1 so that we can sit in with 1 plus TB of the data, and we can just try our logic what we are running up, whether that is suitable for to really run on the real data. So it's all, everything is configurable. You can change everything. You can even change the replication factor to 1. So in that case, your one block is available. One copy of the data is only available. So rest nothing is available. So you can do the testing. So everything is configured.
So if disk 9 or server 9 is where the block is sitting, the data block is sitting, and it requires that server 9 requires logic. How does it know that it is on server 5? It will again go back to the name node.
Yeah, name node.
And then get, okay.
It's reading from the SDFS. When I'm saying it's reading from the SDFS, practically name node is telling me where my data is lying.
Yeah, okay, perfect.
So here it's reading. So this it's getting it from DFS and it's getting it to the local disk, and then it's reading from the local disk to initiate the JVM.
Okay.
Any other questions?
No, not at this time.
Okay. So we just looked at the job tracker. What I was just talking till now is being precise on the slide. Master nodes run the job tracker instance, and the job tracker right now would be again a kind of single point of failure if that goes down, because that maintains the whole metadata which job is running where, and it keeps on maintaining the task trackers state and things like that, and all the jobs which are submitted as added to its queue only. So if job tracker goes down, again it's difficult to reinitiate the system to the same state, although it's persisted, but again the data do not work at the microsecond level. So to overcome this thing, there's little changes in the architecture in Yarn. We'll talk about that part. And it basically determines the execution plan, do all the booking activity for you, to divide up, so basically distribute the whole processing to different data nodes and things like that. And if you're, it also has pretty everything is there defined for you. So if say this data node was running the logic for block 1 of some file, and this data node while running it got up. Sorry, this is job tracker. Sorry, not this node. this data node was running for some block, say block B1, and while running up, there's some error which comes up. So this task tracker will send the NRB signal that the process failed in between, that particular JVM failed in between. So job tracker really keeps maintain that state, and later on, if the same request comes up, if the request comes up for the same block, it will not send it to this data node. It will try to send it to some other data node only. And it also will send for this particular block and for this particular corresponding job which is right now running up to different data node also. So everything it takes care of everything at the back end. So when you run your MapReduce job, sometimes you might see that it get failed, but it's again retry. So everything, all of that retry happens with the help of job tracker, which really maintains or tries to run your job on the different blocks which are available in the cluster.
Yeah, makes sense.
Task tracker really runs on your data nodes. So these are the worker processes which really works for you. So they really run your mapper and reducer logic into the corresponding JVM. And each task is spent to multiple JVMs. Now you know the region, and they constantly communicate with the job tracker. Now you know the reason. If the job tracker fails, so again, this is all I've talked about.
And job tracker is the one which is collating all these blocks which are coming from different data nodes.
Okay, so practically that is not happening. The MapReduce framework will really make you understand. So practically there's a data transfer which really happens over the network, which comes out of the mapper phase. And once you understand the MapReduce architecture, your question would be answered.
Okay, I'll wait.
So heartbeats, both the data nodes as well as the task tracker, they keep on sending the heartbeat signals to the corresponding master processes. Replication failure, I've already talked about. If there's some failure, communication failure between the data node and the name node, or the data node itself is down, the replication factor is maintained in the cluster by the virtue of the name node. Okay, so this is the right architecture. I think you had some question on the right. I forgot the question. Okay, let's see if your question is not answered. We can look at that. So when I as a client send a write request to the cluster, that so basically the first request goes to a name node. Name node returns me where to write that write the individual blocks of the file. So it just returns me the data nodes, say data node 1, data node 2, and data node 5. Go and write the first block to these data nodes, and second block and third block, and so on. So I, as a client, then it's my responsibility to send a write signal to the corresponding data node. So say for block 1, it has returned me data node 1, 2, and 5. So I, as a client, will, and it also returns you where to write first based on your nearest availability and things like that. So I, as a client, will just say a write request to data node 1. Data node 1 will send a write request to data node 2, and data node 2 will send a write request to data node 5. 5 will send an acknowledgement to 2, 2 will send an acknowledgement to 1, and 1 will send an acknowledgement to your client, and the complete signal is then sent to name node, and the name node knows now that the block has been correspondingly placed, and the name node maintains its corresponding metadata, updates the corresponding metadata. Now I think
so this is a multi-phase commit, right? In the sense, unless all 3 blocks are written, the transaction is the transaction of writing the block is not complete.
So there's something called minimum commit. So okay, the default one is 1 in the cluster again. So I've said this write is failed, or before that, say this write is failed before that. So this data node now knows the copy need to be sent to data node 2 and 5. This will communicate to this one. This will send an acknowledgement to this one, and this will send an acknowledgement to this, and this will send a complete signal to name node. Name node at the backend will try to replicate the third block to some other data node which is up.
Okay. Okay. But then it did not. But that may happen at a later point in time, right? Not instant, before the signal to the client is sent saying data node or data return.
Yeah, so say this acknowledgement failed, yeah. This is what you're saying, right?
Yeah.
So in that case, it will assume that the data is not returned over here. If it does not receive the acknowledgement to the predefined frequency, again it will assume the data is not returned. And to the data node, the complete signal will just say data node 1 and data node 2 had that copy. The 5 we are not able to successfully do it. So although the block would have been created, but that will be garbage collected later on because that block is not there in the metadata of the name node. Not
Yeah,
garbage
but then the
collected.
client, what will the client get? Client will get a signal saying data return, or
Data written with the corresponding states.
okay. And then that third, it may means the name node may find another data node where it will
Yeah.
replicate that third one,
Yeah. So name
which
node will
can
later.
take some time.
Yeah, name node will later on send a write signal to either this or this, and they will then copy it to some other data node later on,
But then
transparently.
the client process, which is requesting the write, it can proceed further even if only 2 data blocks are
Yeah,
written.
yeah, but the minimum one is one. If the first one is written, it's all done for the client person.
Oh, so client doesn't really care about the replication.
Yeah, yeah. It's the duty of the name node. It's not my
So
duty.
so minimum number of nodes where the block should be written is really only one.
It's by default one. Again, you can change it.
Okay. Okay. Okay.
So this is the data pipelining which I just shown to you. And to read, it's pretty simple. You get from the name node where the block is lying, and you keep on reading from the data nodes.
Yeah.
Data correctness. So your blocks also use there's something header of the blocks which contains your checksum of the data. The algorithm which is used is C32 algorithm which contains your checksum of the data, and there's a frequent backend checksum which keep on running on your blocks. So if some blocks get corrupted, those are backend automatically replicated by to the other data nodes by the virtue of the name node backend processes. So this checksums also keep on running at the backend. Also, when you read the file, you also check the checksums. If you find a block corrupted at that time, also the job tracker assigns those corresponding things to other data nodes.
Can you go back to the previous slide? Not
Yes,
done. Right one. Yeah. Now, if it has written on D1, and then the client goes ahead saying the block is written, and before that block gets replicated to D2 and D5, D1 goes down.
Sorry, it's written to D1.
It is written to D1 now, and it has not yet written to D2 and D5, but the client gets a signal because it is written to one data node. It gets a signal saying write complete, right?
So this is a pipeline. So data node 1 will send a signal to data node 2, and if the data node is 1 while sending before sending a signal, the signal will not go to this data node, and the client
No.
will.
What I'm saying is that pipeline returns the acknowledge does not come back from data node 2 and 5 because there may be some problem with those nodes, right? There
Yeah,
could be.
yeah.
And so basically the name node gets the information that data is written to only D1
Yeah,
and not to D2 and D5. But
yeah.
because it is written to 1, which is the default, it sends a signal to the client saying data written, and then in the background it goes ahead with its job of replicating at a later time whenever it feels correct, right? By finding a, but in the meantime, if D1 goes down, now the block is not there to replicate, but the
Yeah,
client
yeah, of
already
course.
got the message. Client already got the message block written.
Of course, that's the disadvantage of default one. Such a scenarios you have to handle with replication factor of 2 or 3. Definitely, that's a disadvantage of replication factor 1.
Okay. Means minimum right to 1
Yeah.
is not really recommended as such.
Yeah, but that's a default one again. And
Okay.
that's a
Okay.
disadvantage of minimum replication factor 1, yes.
Okay.
But the probability of that thing is very less because your data is copied to three at a time. So all the three at because name node knows these three are up. When the name node returns in him, that copied to these three, because they have just sent the heartbeat signals to the name node last few seconds back only. So they are up. Probability of them going down in just fraction of seconds very less. So practically the write will happen to all the three only because name node knows they are up and they were up just few seconds back. And even though one can go down at a time, two different tracks again going down at the same frequency of seconds again very less. So probability of that thing is very less, but yeah, definitely there is a disadvantage of replication factor 1.
Yeah, I understand. Okay. Means the chance of that happening is less, but
of course, yeah, it's there. The whole two racks
no,
connected.
in the sense you have to really think based on the criticality of the data, right?
Yep. So again, the people are maintaining the transactions on the Hadoop-based system, but still the frequency of people who are really doing the transactions on the SDFS or Hadoop-based systems is very less. These systems are used to process your enormous amount of data and do analytics and creating star schemas or creating data warehouse processing and doing ETL kind of things on the data.
Yeah, other similar databases use a term eventual. I think
eventual persistence.
Eventual persistence, right? Means eventually it will be all replicated, but may not be on that point.
Yeah, the Cassandra does it.
Yeah, okay. And even MongoDB. Okay.
Yeah. So that's all for this thing. Any questions? Anyone else? I'll answer that zookeeper part tomorrow. Let me open up with the picture also, and let me also cross check that part because I'm also not 100% on that part.
Yeah, I just put it in the chat.
Yep.
No, it's a good lecture, and I'm happy. You are a pretty patient person, so which I like.
Sure, thank you for that. So people keep on saying that I go very fast. So whenever you think I'm going fast, just do let me know, because I just when I start speaking, I start speaking at a very fast pace. So just let me know whenever I'm going fast, so that automatically comes up. But I try to.
Yeah, it all depends. Suraj, what do you feel? Because I don't want just me talking, because I have tendency to talk.
No, it was good. It was really good. Like for me, like it was like different, little bit different. Like my thoughts were like little different about that. Not done much of studies on the database side, so it was really good.
Yeah, but the speed is okay with you, right?
Oh yeah, like it was a little fast, but like he himself knows about it when he said like he will stop and he will explain. When the processing, like when he was about to explain the task things, but which I like, not a problem. The speed is okay for me.
Perfect.
And normally like we Indians are little fast.
I agree with you.
Oh yeah, in this class all are Indian. Okay, so all of you know Hindi.
Oh yeah.
Very good. Yeah, very
okay.
much.
So when they are most of the times, most of our students are from US only, and in most of the classes there is one or two people who are from UK or US background or Italian kind of thing. In that case, I don't use Hindi. But if there's all Indian, I sometimes use. I prefer to use sometimes communicating in Hindi also. That makes understanding. Yeah.
Yeah, I'm originally from Pune, so I'm okay with Hindi.
I'm frequent visitor to Pune also. काफी request आती Pune में training की, so I keep on waiting for it.
Oh, okay. You are somewhere in north, right?
Yeah, I'm in Noida only.
Noida. Okay.
Okay, so let's meet tomorrow at the same time. Any other questions which you have? Anything else?
So Miraj, like you were saying that like the data, the program that you're going to give us, like the file, the jar files and everything, it will be like 5 to 6 GB. If you can send it to us, then we can start downloading it.
Yes. So you will receive a request on our Gmail, shared folder, 2-3 different folders will be shared up to you. One will have the PPT. So as soon as I'll be completing the whole topic, I'll be sharing the PPT. The PPT जो मैंने आज which I've discussed right today, I'll be sharing that thing. And I'll also share all the software which you can just download it. We'll look at that part tomorrow, how to install that part. And and so Mahesh, Suraj is flying to India and he wanted to cover up the course in Three and a half kind of weeks. So are you okay with some of the classes on the weekdays because we are just three of us? So I am flexible or to take that part of a little bit some extra.
No, I'm perfectly okay. If I know in advance, I'm perfectly okay if it is in
Okay.
the evening, because if it is in the afternoon or something, it will
No,
not be possible.
it will be on your evening only, around similar time, or a little bit
Yeah, then
half an hour, 1 hour up and down kind of thing.
yeah, then I'm perfectly fine.
You know, Miraj, Mahesh has a very good timing.
Yeah, means actually it's tough for Suraj because he's on East Coast and it is
Acha, Suraj is
practically
on his
12.
stuff. Okay.
Yeah, because it is 12 o'clock for him
Okay.
in the night right now. So
And that
that's perfectly fine. It's evening and weekdays, absolutely okay with me. No problem.
Oh, okay. Yeah, we can have it little earlier also because I can wake up at 6 only. It's summer. So yeah. ठीक है.
Yeah, yeah,
Um,
I'm flexible. I'm flexible.
okay.
yeah, रात को पढ़ाई का आदत नहीं रहना थोड़ा.
And ठीक है, कोई दिक्कत नहीं है, इसको कल देख लो, वरना we can maybe even prepone it for half an hour, 1 hour also. That's not a problem to me.
No, like it's okay, like that's fine. Miraj, like आपका email address भी भेज देना.
हाँ, yeah, I'll ping it on right now on the chat window only. It's miraj@design.pathshala.com.
Oh, it's simple.
You can directly communicate me on this email with any of your queries or anything, or if you don't get files or anything, you can just drop me an email.
So as far as the installation of the software and all, you are going to explain that tomorrow,
Yeah, I'll
right?
explain you everything, and that's also written over there. But I'll explain you everything, and then you can try it out on your laptop. And you have the laptop with at least 8 GB RAM, right?
Yes.
Yes.
Yes, ठीक है. क्योंकि 4 GB में थोड़ी फाइट हो जाती है चलाने में, फिर your system goes very slow. So
Yeah. No problem. 8 GB is not a problem nowadays.
yeah, that's by default 16 GB which is coming up now.
Yeah. Okay. All righty.
Okay,
Talk
then.
to you tomorrow.
See you
Yeah, have a
tomorrow.
good day.
Yeah.
Okay,
Talk
good
to you
night.
tomorrow.
Bye bye.
Yeah.
Good
Bye-bye.
night.